Hi, Doc Revis here. In this video, I'm going to show you how to draw Lewis structures, and for this video, we're going to limit that to single bonded compounds. When we consider Lewis structures, we note that valence electrons, or Lewis dots, combine to form compounds that fit the octet rule of 8 or other stable configurations based upon the element's position on the periodic table. When we say that, what we mean is that typically compounds will have 8 electrons surrounding them, especially when they're found in group 14, 15, 16, 17, and 18. Otherwise, in group 1, we will have 2 electrons surrounding them. In group 2, you'd have 4 electrons surrounding them. And in group 13, there will be 6 electrons surrounding them. We show you the valence electrons in blue here on this periodic table. In order to teach the concept, we're going to use methane as the example. So let's get started with methane. If we consider methane, methane is composed of 1 unit of carbon and 4 units of hydrogen. Carbon has 4 valence electrons and hydrogen has 1 valence electron. Carbon is the central atom. It's located in group 14 or group 4A. We look at how these dots surround each of these elements. In the case of carbon, it completely surrounds them if we consider carbon to have 4 sides, and hydrogen has 1. And so the primary Lewis dots for carbon and hydrogen are shown here. So how do we draw these? Well, there are 3 rules that I'm going to teach you. 1, draw the valence dots around each element assuming 4 sides. The summary of that is shown on the left and right side of this slide, where we have hydrogen that has 1 electron, 1 dot, based on its position on the periodic table. And on the right side of this slide, we have carbon, which has 4 Lewis dots around it based on its position on the periodic table, group 14 or group 4A. Next, we will extend lines from each of the dots, only as a way to help focus on where the electrons will align for bonding. We would then take these extended structures and attach them to the central atom of each proposed compound. If we do that, what we discover is an overlap structure as shown here. So in 3 steps, we now have a basic Lewis structure for methane, which has the tetrahedral geometry. We simplify that by showing you here on this slide. This is a cleanup version of methane Lewis structure. When we look at it, there are at least 3 different ways we might draw these, or authors might draw these. Figure A, B, and C. They're all correct and they're all allowed. These are synonymous structures because one line represents 2 dots. If we look at the central atom, we'll note that there are 8 electrons around the central atom, which fits the octet rule. And we note that for hydrogen, which is located in group 1, we have 2 electrons, and therefore that is a satisfied structure for the overlap of orbitals when hydrogen is bonded to carbon. And this is what it looks like when it's all cleaned up. Tetrahedral structure of methane. Let's take a look at another example using ammonia Nh3, which has 1 unit of nitrogen and 3 units of hydrogen. In this case, nitrogen would have 5 valence electrons and hydrogen, of course, has 1 valence electron. If we use the rules where we draw the valence dots around the elements, we would note that nitrogen would have 5 electrons around it, 2 of which are paired to form a lone pair, and the lone pair does not participate in the bonding. If we extend the lines from hydrogen and nitrogen as shown here, again, this extension of the lines is only to show where the orbitals will overlap, and when we do that, we end up with a pyramidal structure of ammonia as shown here. And if we clean that up, we see projection A, B, and C, as the final Lewis structures with a lone pair on nitrogen. It should be noted that nitrogen conforms to the octet rule of 8 as shown on this slide, and hydrogen forms a stable bond with nitrogen containing 2 electrons based upon its position on the periodic table. Another example would be ammonium fluoride, shown here. We would, step 1, draw the dots. Step 2, extend the lines from the unpaired electron, the unpaired dots, and we overlap and we get the pyramidal structure of this as well. And the cleanup version of this, A, B, and C, shown on this slide. Note here that in this case, nitrogen conforms to the octet rule, and so does fluorine, which contains 3 lone pairs of electrons. Let's consider water. Oxygen is located in group 16 or group 6A and has 6 valence electrons. Hydrogen again, of course, has 1. If we follow the rules, draw the valence dots, draw a short line, a bond from each dot, an extension of the dots to show where the orbitals overlap, and then attach the bonds to each element with the central atom taking the majority of the bonds, we would get a bent structure for water as shown here. And if we clean that up, we have the structures shown here with B in the middle, and we have A and C on either side. All 3 of these forms are permitted as Lewis structures of water. Oxygen has 8 electrons and therefore fits the octet rule of 8, and hydrogen has 2 electrons and is stable configuration for its location on the periodic table. Moving now to group 13, which is 3A on the periodic table. We have chlorine, which would have 7 electrons, which would consist of 3 lone pairs, and we have boron, which would have 5 electrons consisting of 1 lone pair. In this case, boron is the central atom. If we follow the rules through by adding the dots, which represent the electrons, and then we extend the lines from each of the unpaired dots, which represents the orbital overlap region, we would get a structure that's trigonoplanar as shown here. It should be noted, however, that this projection is not quite an ideal drawing. In fact, the 3 bonds around boron will be equally distributed. If we clean that structure up, we have the structures shown here, A, B, and C, which are accepted representations of the Lewis structures for boron trichloride. In the case of boron trichloride, boron only has 6 electrons surrounding it. But because it's located in group 13, this is a stable structure for boron having 3 groups attached to it. In the case of chlorine, it is located in group 17 and would have 8 electrons to conform to the octet rule. So what we have here is an example of where the central atom did not have 8 electrons, but was electronically stable with 6 because of its location on the periodic table. To finish this, let's consider group 2 and group 1. In this case, we use examples of magnesium. We have magnesium and the 2 chlorines coming together to form magnesium chloride, and then we have sodium coming together with chlorine to form sodium chloride. In the case of magnesium, we have 4 electrons surrounding it, which is stable based upon its position on the periodic table. In the case of sodium, we have 2 electrons surrounding it, which is stable based upon its position on the periodic table. And of course, all of the chlorines have 8 electrons, and therefore we have a very good Lewis structure for these compounds. There you have it, a method of drawing Lewis structures for compounds containing single bonds.